So let's start. This is the second part of centralized convex machine learning, essentially mainly convex optimization. Here in this lecture, we will see a little bit more connections to the setups of machine learning, how we can work with data sets and all those kind of things. And then here you will see the first two computer assignments. Okay. First, let me recap a little bit lecture 2, and then if you have any question remain from lecture 2, I would be happy to answer if I can. Okay, well, again, the learning outcomes here. First, we will start with a recap of deterministic approaches, so the things that we have seen in the previous lecture. Again, main definitions here. There are going to be 2 more definitions here. We need them for this lecture. Then a stochastic optimization, the general setup, the reasons behind to go with the stochastic gradient instead of, well, stochastic algorithms instead of deterministic algorithms. And then saying that they really suffer from high variance and how we can do variance reduction techniques. And finally, some form of convergence analysis. Just to get some insights of the convergence rate that you're going to see if you go with the stochastic gradients. Okay, so let's start with some basic definitions. Not basic definitions, essentially a recap of lecture 2. So in previous lecture, we have seen a lot of different optimization algorithms. Actually, you didn't see acceleration methods. There were no time to say that. But generally speaking, we can go with 2 different categories. The first one is if we have a smooth problems, or if we don't have that smoothness, so essentially called non-smooth optimization problems. If we do have a smoothness, so the function is L smooth, it could be strongly convex, mu strongly convex, it may not be, but the only thing that we do need to be able to run all these things is essentially the availability of the gradients, okay? So if the gradients are available, then we can use gradient descent to minimize an unconstrained function. So W will come, the optimal solution will be in this RD anywhere. And if we do have a convex optimization problem, then the iteration complexity is in order of 1 over k, okay? So sublinear convergence. On top of that, on top of this convexity, if we do have a strong convexity, you have seen that we can have a linear convergence. Essentially, instead of having O of 1 over k, we do have O of c to power k or e to power minus ck. Both of them are the same, okay? Then what would happen if we have a constraint optimization problem? So again, the same thing. So the function is smooth, it's convex, so the gradients exist. And if we do have a constraint here, then we're going to go with usually projected gradient descent, okay? So easiest thing to do. Then on top of that, if that smooth problem, convex problem happens to have a very bad condition number, so L over mu is very large, so essentially it's not a round sublevel set, it's really skewed, then in that case, we can go with a steepest descent to precondition that geometry of the optimization. So this is the logic behind all these algorithms. Then on top of everything here, if we do have access to the second gradients, so the Hessian, and then if it's of low complexity, to find the inverse of that Hessian, you will see that you have seen probably that in homework 1. Then in that case, we can use Newton methods to have a geometric convergence, so extremely faster convergence rates. That works even for ill-conditioned problems, so large L over mu. And on top of everything here, if due to any reason we don't want to go with second-order methods like Newton methods, there are a way which are usually called acceleration methods. The most famous one is Netzroff acceleration, where you can use to find the best rate, which is O of 1 over k squared. And you can show that this is the best rate that you can achieve, okay? So you will see a form of acceleration method here. Okay, so I will say what it is. But what happens if the problem is not smooth? So if the function is not smooth, then what happens is that the gradients are not defined. So in that case, we still can use all of them, but we need some form of modifications to be able to run those gradient descent, because the gradient descent, the steepest descent, projected gradients, all of them requires a form of gradients, and we don't have gradients. So in that case, there are at least 2 different extensions of the gradients, or modifications, or let's say generalizations. The first one is to go with subgradients, Okay, and in that case, we can use exactly the same algorithm as gradient descent, just replace gradient with subgradients, and there is a definition of subgradients. You have seen that in lecture 2 in Food for Thoughts. So that's the definition of subgradients. And subgradient doesn't have to be unique. Of course, depending on the subgradient that you choose, the performance could be different. But usually, the convergence rate is of the same order as the actual gradient descent. And there is another generalization, which is called proximal methods, that works pretty fine if the optimization structure, instead of being of this form, if it is in this form. Okay? So what is the difference? The difference is that if you are given just one f of w, you cannot do anything. But then if it happens to you that you know that f of w is of this form, which is pretty much the case in most scenarios. For instance, just assume that this is your actual objective function, and then you can define the loss function to have your smoothness, whatever you like, and then this is the regularization or whatever, okay? So in that case, the non-smoothness part comes from this h, and then we can define the proximal operator and then run the proximal methods. Essentially, this is another generalization of the gradient. And then the whole algorithm is almost the same as the gradient descent. The main difference is that you do gradient descent on this, and instead of running the gradient, you run something called generalization of the gradient, proximal operator on that. And then what happens is that if you are not happy with this convergence rate, you can improve that by using a form of acceleration. So it's, again, the same ideas. Of course, you can use a steepest descent here as well. Nothing is fundamentally different. So if the optimization landscape is not good for you, you can change the geometry by finding those preconditioning vectors. One of them is like acceleration methods, where usually you do have two steps in the iteration instead of one step. You have the usual proximal iteration, but then before doing that, you do have something called momentum, where essentially what it does is that as iteration goes and goes and goes, you will put more and more weights on some parameters that are not changing, okay? So if I give you an example, then if the optimization is like this, the landscape, then this is wk k minus 1, let's say, and this is wk, okay? And then in these two-dimensional things, wk, let's say wk minus 1, 1, wk minus 1, 2, and wk1, wk2, okay? So this is vector wk minus 1, and this is vector wk. What happens is that here, these values are not changing so much, okay? So what it means that after running these iterations, then we are not changing so much these values, so the second elements here. Because if this is wi1 and this is wi2, right? So we are not changing the first element so much. We are changing the first element. We might be able to change that, but then we are not changing the second element so much. So this is what happens here in this momentum. So you are putting more and more emphasis on the second element to say that let's not change that so much, but then change the first element so much. So essentially what it means that the actual gradients that you're going to find is going directly toward that direction instead of oscillating here, okay? If you think about this, then you will see what I said. Yes, with that trick, well, the thing is that here you need one memory to save this one, but that's fine. But then with that simple trick, you can observe almost this convergence rate, okay? So this is a recap of the algorithmic part. But some recap about the main definitions that we had. So we had 3 main definitions in the previous lecture. The first one was the definition of convexity. So the first one here says that essentially the change, if the function is differentiable and convex, then if differentiable convexity means that the change in the function will be larger than a linear approximation or a linear function. So here we have a linear function, and here we have the change in the function. So the change in the function would be greater than a linear function. If on top of that we have a strong convexity, then the change of the function, move that here, so then you have f of w2 minus f of w1. So the change of the function gonna be greater than a quadratic function, okay? So this is what it says, a strong convexity. What happens if mu goes to 0? you have a strong convex function, but it just doesn't matter because you have a very bad lower bound to say that the change of the function is lower bounded by that almost linear function anyway. So for a smoothness, you can say f of w2 minus w1. So the change of the function gonna be lower bounded by another quadratic function with curvature L. Okay. So these are the main definitions that we had for bounded error. So these are two main definitions that we're going to need here in this lecture to establish most of the convergence results. So the first one is a bounded error and the initial guess. So, and then it can be easily satisfied if we say that the set of all the samples are coming, not all the samples, all the parameters that we are looking for are within this compact set and bounded set essentially. So it will automatically satisfy that. But then it essentially says that there are some randomness somewhere, you will see that later on, and then expectation over all those randomness, initial guess minus the optimal solution within whatever the region over which you're optimizing, it should be smaller than error. So from the beginning, you are within that ball of radius R, and usually it's defined in terms of norm 2. It doesn't have to be. But for this result, we need to have that in norm 2. Okay? So as it is clear, perhaps, it just says that this is W star, and W1 is somewhere here, and the radius here is R. So this is W1, somewhere here. The second one is Lipschitz continuity or bounded gradients. So it says that if we have a bounded input, so bounded W or bounded parameter, then the gradient's going to be bounded by some beta. Okay? And why is it important? Because it automatically says that if we limit ourselves to search within this, then the gradients all over this bounded set gonna be bounded. Okay? It doesn't have to be bounded everywhere. It just have to be bounded over the search area that we are looking for, which is this search area. Okay. And then you can easily show that this can imply this one as well. They are the same definitions. Just to make it a bit more clear, this is Lipschitz continuity, a smoothness, also called, if you recall here, you can just replace these two with gradients, and then you see the definition of a smoothness with L a smoothness. Just replace B with L, replace these two with gradients, and then you can recover definition of a smoothness. So that's why a smoothness is actually Lipschitz continuity on the gradients of the functions. Okay. That's why it's either called a smoothness or Lipschitz gradient, Lipschitz continuous gradients. So both of them are the same. So the first example where you will see some connection of whatever we said on real machine learning. This is the setup of the problem, you can see, but just to say the importance of this problem, so there is a data set where you can easily find in the internet, download that, and then there are descriptions of the inputs, there are some outputs, just look at these two outputs. So either moving or not moving, and consider this objective function with that definition of f of I. We don't use classification here, so the task is not to train that model, it's just to find the hyperparameters that we're going to need for the optimization things. But if you do like to do the classification, you can easily train this model using that data set and then use sign function to find the outputs. Okay, this is very easy to do. In homework, you're going to find what is the main reason behind this homework. In reality, you will not given any of these parameters in this inequalities here. And then you have a lot of bounds. What is this bound as a function of L, as a function of mu, R, B, and then you are not given those parameters, okay? And usually you are very sensitive to the choice of those parameters and you cannot choose anything that as you like. So here is a small example to ask you to think how you can find those given some real machine learning problem, some real objective function and a data set. Okay, so some remarks. The first one, it says find if f, which is here, Lipschitz continuous or not, so the last definition, and if so, find a small b. What is the reason to say a small b? What would happen if we don't have that small? I didn't put minimum here because it's going to be tricky, but then just a small would be enough. And you will be judged of if this is a small enough or not. But try your best to find the smallest one as you can. But then why a small? What would happen if we go with a large? Is it trivial to find a large one? Okay, I will recall you the definition of B here. Okay, what would happen if we don't put that limit? Then a trivial bound on B is infinity, right? You can always say that the gradient is smaller than infinity or extremely large number, and then you're pretty sure that all the functions, as long as the gradients are defined, which is defined for that f, then you have that bound. But is it useful? No. Why? Because in most theoretical analysis, you will see that the convergence rate is a function of B, and you will choose some very extremely large B, so overestimate B, and then you will wonder, the bound says that the convergence should be smaller than this, and then I can achieve this accuracy after 1,000 iterations, but in reality, I will see after 10 iterations I can converge. So what's the problem here? The problem is an overestimation of B. So the bound that you're using is not tight due to a bad choice of B for yourself. Okay, so this is the reason behind the small. Then Fi is smooth or not, and then find a small L for Fi. Why a small L? Same reason, right? So we know that the function is like this. So this is our f of I, for instance, and then this is L, a smooth function with parameter. Of course, you can say that L can goes to infinity, then you're gonna have something like sharper and sharper and sharper here. Well, everything should be from here. It's going to be sharper and sharper, but it's not useful at all, right? Because you can always say that this will be upper bounded by something like that. And it's not useful at all. So closest to the curvature of the actual figure, the better. The next one is f strongly convex or not? And then find high mu. High mu means that this is the lower bound with curvature mu, and then try to make it as close as possible to the actual f. And if you can do that, then the bounds that you're going to have, performance bounds, going to be tighter and tighter. Okay, try to find these parameters here for this. Let's start with the definition of f of w being 1 over n summation of fi, and for the sake of simplicity, assume that n is finite. So we have a finite sum objective function. So recall from lecture 1 why we are interested in this form of objective functions. If you recall from the expected risk, we have expected risk, which should be expectation of fi, essentially, well, expectation of f of w over some randomness. And we don't have that distribution, and that's why that we are going with empirical risk, and this is usually the definition of empirical risk. So this is what we will see in most of these empirical risk minimization. That's why that this form is particularly interesting for us. Okay. But then what happens is that, so we have this, the gradient is very simple due to linearity of this operator. We can say that 1 over n summation of gradients of f of I. So this is our gradient with respect to w. And then we can run the batch gradient descent that we have seen so far in previous lectures. So this is a completely deterministic approach here. A stochastic gradient, on the other hand, says that we have a bunch of samples. Well, n doesn't have to be sampled, but we have a bunch of f of I, and all of them will contribute to this sum, to these gradients, okay? Just take one of them at random, the simplest version of a stochastic gradient, let's say vanilla gradient, stochastic gradient. In that setup, it just says that randomly pick one of those indices and do this iteration. So wk plus 1 equal to wk minus alpha k, some g. Okay, this zeta k is just a random index within set of n. So here you can see that, okay? And this is a noisy version of the actual gradients, we call it. What is the exact value of this g? It remains here because we can have different versions of that depending on the algorithmic approaches. But all of them, what they do is that this g gonna be an approximation of the actual gradient. And again, we know that the actual gradient is 1 over n this summation here. So the whole idea is somehow approximate that using some call to the oracle. What is the oracle? Let's say that there is an oracle that you will give an index, and the oracle tells you the gradient of that index, okay? So you will ask oracle, give me the gradient of f of 2, it will give that. This guy requires n calls to the oracle because we need all these gradients to be able to find this. This guy may need to find just one call. Okay. So this is a general setup here. Then just for sake of comparison, we have in gradient descent, which is usually expensive iteration cost. We need usually, this iteration cost is usually linear in n because we're gonna need n times computation here, but then few iterations are fine. Well, just recall that few depends on the geometry of the optimization. It could be pretty large, but then there are some ways to handle that. And few means compared to this guy. Here, usually we do have very cheap iterations, usually independent of n. Just assume that this zeta here is just one index. And if it is one index, then it just randomly select one index independent of n. Okay? But then the problem, though, is that we have a lot of iterations we will see to convert. So the way that it behaves, if we just go with one gradient, is like that. In a usual gradient descent, the convergence is like, let's say, going with this landscape. Let me write it here. So the gradient descent is like this. It's going to converge. But a stochastic gradient behaves like that. So you have some randomness here. And at the end, it may not converge depending on the choice of, you will see, depend on some parameter. It may not converge. But it can converge to some ambiguity ball, and that's it. And the radius of this guy will be determined by some noise of this estimation. So you may not be able to converge, but then you can converge to something, and then you can control the radius of this ball. Okay. But then there are lots of randomness here. So the main question that you will see in this lecture and the following lectures, well, not in the next one, but then afterward, is addressing this trade-off. Per iteration cost and per iteration improvement. Okay? So the whole idea of those variance reduction thing is just to address this trade-off. Okay, I guess that I said some of them. So let's go with some benefits of a stochastic gradient. If you now pick almost any paper in machine learning, not any paper, but most of them will really, they are applying some form of a stochastic gradient now instead of gradient, the vanilla gradient descent. And due to some of those reasons, okay? Especially in deep learning, usually they are always working with a stochastic gradient kind of forms. We have very good theoretical bounds for the stochastic gradients. For instance, for strongly convex and smooth functions. For gradient descent, we know that this is of this order, okay, for some rho. And it means that we need n log 1 over epsilon total work because we need this amount of iterations, and per iteration we need n work, so n call to the oracle. For epsilon optimality, for a stochastic gradient, we will see in the next lecture, in the next slide, that the convergence rate, first of all, we cannot have this deterministic convergence because there are some stochasticity in the process. But the expectation of that error or difference to the optimal solution gonna decay with this order of 1 over k. So we don't have this linear convergence. This is sublinear convergence, but then we need 1 over epsilon total work from this for for epsilon optimality because we need this amount of iterations, and per iteration cost is just one call. So then it depends on the value of n. We can say that n log 1 over epsilon could be larger or smaller than 1 over epsilon. This is a very simple comparison. You can't really measure the complexity of the whole thing's computation by just these simple meters. But then this is good enough to build the intuition. So depending on the regime, on how large n is, we may even go with a stochastic gradient and have a better convergence in terms of time. Okay. The other reason to go with the stochastic gradient is with large scale optimization. If we might have some large matrix inversion somewhere, depending on the version of a gradient descent or steepest descent in general, which we may not have in a stochastic gradient. So again, per iteration cost is very, very cheap and really scalable for large scale machine learning. Heavy communication we might have for gradient descent. We will see that. Just imagine that these gradients here, will be computed by different workers. So imagine a master worker kind of primal dual iterations where there is a master node and there are some workers, and those workers, they will compute these gradients for you, return them to the master node, okay? So per iteration, it's not just n computation, it's also n communications. And then usually you will see that if n is large, then that communication really would be the main bottleneck of the whole computation process. The whole convergence time, essentially. So if we do have especially some bandwidth limited distributed optimization, then usually stochastic gradients may behave much better than the normal gradient descent. There could be some security. We don't want to reveal the gradient, but then we can reveal some noisy gradients. This is good for many different versions of security, like differential security, differential privacy things. And then finally, this is among the most important one, especially in deep learning, is non-convex optimization. We will see in the next lecture that if we run a stochastic gradient is much more robust to the saddle point and much more efficient to solve non-convex optimization than gradient descent, due to exactly that randomness. That randomness is really crazy here, but then it's really beneficial in the non-convex regime to escape these saddle points. Okay, so there are just some reasons here. Here you can see some a very generic stochastic gradient form for decentralized optimization is called. We will initialize W1, and for sake of mathematical analysis, we know that W1 should be within some bound of the optimal solution. Okay, that R could be very large, but then we know that it's within some bound. Okay, and then for every iteration, generate a random variable zeta, usually IID random variables, IID over time, so over k. Then compute a stochastic vector here. We will see later what is this stochastic vector, but in the easiest form, which is here, a stochastic vector is just the gradient of that spatial index. So just create one random index, get the gradients of that random index, and update based on that one gradients instead of based on all n gradients. Okay, choose some step size. We will see that all the convergence is a function of that choice essentially, and then finally do this very simple first order update, which is wk plus 1 wk minus alpha kg. Okay, examples of a stochastic vector. So for these stochastic vectors G, we can have at least these three examples, but we're going to see some more examples as well. So the first one is gradient for just one sample. In that case, that G is essentially gradient at some random index. We can have a gradient for a mini batch where you're randomly, instead of selecting just one sample, you're randomly selecting some samples, let's say in that case, nk samples. So you subsample the original data set, for instance, that you have a data set of size n. You will subsample them with nk, and then find the average of the gradients, or an estimation of the average of the gradient based on this mini batch sampling. So like Monte Carlo approximation of this gradient of this, okay, with nk samples. By the way, if the noise of, let's say the variance of the noise of the gradients, what is that? The variance is the variance of this G. Okay, if the variance of G here is sigma 2, here if it is sigma 2, then for this guy, you can show that this is sigma 2 divided by nk. So the variance will be reduced, and we will see later on that this ambiguity ball will be determined, the radius of this guy will be a function of this sigma 2. So what this suggests is that you can add a little bit more computation or communication depending on the decentralized version or a centralized version. We can add a bit more computation to compute that for nk and linearly reduce this ball here, the radius of this ball, and then make sure that we can somehow converge to the actual optimal solution, even with gradient descent. But of course, the expense that we are paying here is just more computation. And then if you say that nk equal to n, then you will recover gradient descent. Anyway, as we have seen so far, in steepest descent, this is pretty much the same scenario as a steepest descent, you can precondition with some positive definite matrix here, H. You will see why it should be positive definite. But then as long as you are not changing the direction, you are on the same half space as the gradient, then you're fine. And then positive definite matrix here will satisfy that. So you can do that to precondition the geometry of the optimization if you like. So exactly the same idea as before. Just one note here. We do have these gradients here, and then we don't have any projection here because the underlying assumption is that we are solving this optimization problem. But what would happen if I add this constraint here? So if I add this should belong to W, then in that iteration, I can try to write it down here. Then in that case, I can just write down projection on W of this guy here. Hopefully it works. Okay, that was a bit off. But then projection of the W. So instead of having that, just find that and then project over set W. As long as it's convex, then all the convergence results would be the same. Okay? So again, you can move from this very simple generic stochastic gradient to a steepest version, to the projected version, to the accelerated version, to all those versions. You can do that. Some inequalities here. In the regime of deterministic optimization, those inequalities are just great and insightful. But just in my opinion, the inequalities here are even more insightful to see how we should change actually the parameters and what are the impact of different parameters. So let's start with definition of a smoothness. Okay. We can show, by the definition of a smoothness, you can show that this inequality would hold. So if the function is L smooth, and then if we run these generic iterations here, even if you add the projection here, nothing would be different. Then in that case, you can have this inequality here. So let me first say what this inequality is, and then we can try to even show how we can achieve that. So this inequality says that the expectation over this randomness in the iterations that we do have of f of wk minus f of wk plus 1 minus f of wk, so expected improvement per iteration. This is the meaning of here. Expected improvement is determined by two factors. The first one is an expected decrease. So if you didn't have this term, then you could recover the actual gradient descent of monotonicity of the gradient descent. So if you run gradient descent over a convex function, then and smooth, in every iteration, you can improve your objective function in terms of you can decrease that. So this is the meaning of that. In every iteration, you're going to decrease that if there is no noise. But then unfortunately here, there is a noise, and that noise, just to make sure that this is a positive number, we know that alpha k by definition should be positive, but then this term should be positive as well, right? Then you will see that later in the next condition that we make sure by assumption that this is positive. So gk would satisfy this greater than 0 inequality. Okay, but just assume that this is positive, then the whole term here gonna be negative, so this is expected decrease. But then, unfortunately, we do have a noise, and all the terms here are positive. Alpha is positive, L is positive, and this term here is positive as well. So there is no way that we can reduce this unless we play with these parameters. So the first parameter is just set alpha k grows to 0. Then what would happen? Can we do that? Can we set alpha k to 0 to make sure that this noise is 0? Why not? No improvement, right? So it just doesn't make sense. Can we set L to 0? No, this is determined by the problem structure, so this is not in our hand. We can try to minimize that as much as possible, not minimize. We can try to choose that as small as possible for our specific case, but then usually we cannot do so much about that. But then what about this term here? Can we reduce that or make it 0? We can do that if we are sure that this G is error-free. We can do that. But unfortunately, G may not be error-free by the definition of a stochastic gradient. The way that we create is not having access to the full data. So this is by definition. So you may have some noise. But then all those variance reduction techniques, essentially, they are trying to reduce this term as we go in the iterations. So this is the whole idea here. And then you will see that those variance reduction techniques, how they impact on the convergence rate. Here, there is no convergence rate, by the way. Okay, you will see that later on. But then all the convergence rate result, you can imagine that they are using essentially this inequality here. But then the way to show this inequality is, and by the way, you can show here, that's very easy, that if G is unbiased estimation of the actual gradient, again recall that, so G is an estimator of this guy here. And if it is unbiased estimator, what does it mean? It means that expectation of G, expectation over zeta k of G of WK of zeta k is equal to the gradient of f evaluated at WK. If that holds, so we have an unbiased estimator, then just replace this guy with the actual gradient, because this is unbiased estimator, right? Then you will see something like that. So very easy. So actually, later on, we're going to use these inequalities, because in most of the cases, we're going to assume that this estimator is an unbiased estimator. But then you can see that in some of those variance reduction techniques, like SAG, stochastic average gradient, you will see that later, that this is not actually an unbiased estimator. This is a biased estimator. So then you cannot use this inequality, and you should start from here. But for most of the cases, we can use this one here. Cool. How to prove this? Any idea? Well, the only thing by definition you need is just L smoothness, right? So let's start with the definition of a smoothness, and we have the definition, let's see, back here in this slide. So start with this definition. Instead of W2, put WK plus 1, here WK, so let's try. I'm just starting from that, putting instead of W2, WK plus 1. So f of WK plus 1 minus f of WK greater than the gradient of f at WK transpose WK plus 1 minus WK. And then noting that somewhere here, by definition, WK plus 1 minus WK equal to minus alpha kg of WK zeta k. This is by definition of generic stochastic gradient, right? This guy plus L over half. Yes. No, that should be smaller. This is a smoothness of WK plus 1 minus WK norm to 2. Right? And just replace that guy here. Then here, I'm going to have minus alpha kg of WK zeta k, and then here plus alpha k square L divided by half norm 2 of G of WK zeta k, right? So nothing magic here. And then now take an expectation with respect to zeta k, and then notice that by definition here, condition on WK, then WK is independent of zeta k. This is by definition of independency in random realization of zeta k. And then here you can see that this guy will be chosen after the computation of WK. So WK has been computed in this iteration. In the next iteration, we're gonna compute zeta k. Okay, so WK and zeta k, they are independent. Then it means that zeta k of f of WK plus 1 minus f of WK gonna be smaller than this gradient term here. Well, we do have a minus here, gradient term here, alpha, let me write it down. Minus alpha k gradient of f at WK transpose expectation of G of WK zeta plus alpha k2 L half E. So this term here, nothing here. Okay? And then this is exactly the inequality that we are looking for. Where is it? This is exactly that. So just definition of a smoothness. And then from that, it's easy to show, to come to here, okay? So, some useful assumptions. And you have seen that in the recap slide, so most of them are actually there. The first one is the sequence of WKs. This is just for sake of analysis here. So the sequence of WK is, they are in some open sets. Don't worry if you don't know what is open set, that's okay. So they are in some set, that just doesn't matter so much, over which on that set, f is bounded below by some scalar f of inf. Why we are saying f of inf? Because depending on the algorithm, we may not be able to recover f optimal. It depends on the algorithm. For instance, if you want to run that over non-convex optimization, there is no guarantee that you can recover f optimal. What you can say is that there is an scalar f of inf, and that scalar could be equal to f star. The whole idea here to show that these iterations will converge to f of inf. And if it just happens due to geometry of optimization that f of inf is f star, then you're done. For instance, if it is convex, then f of inf is f star. Okay, so the first one, not a big deal. The second one, there exists a scalar C0 and C such that for all integer k, we have these two. So recall the main things here. So here it says that this should be positive, okay? Essentially, it means that the gradient, the noisy version of the gradient, our estimation should be on expectation on the same half space. It doesn't have a space as the actual gradient. It doesn't have to be on the same half space on all realization. Just on expectation, it should be there. Okay? So this is the only thing that we're gonna need. Why we do need that? You can imagine again from here that we need that. This is exactly this term here. We need that to make sure that we do have an expected decrease. Okay, this is the only thing. And you can imagine that after some points, the gradient is going to converge to 0. So after some points, we don't have any expected decrease, and this is going to be the most term that will determine the convergence. So we're going to converge. From here, you can see that we're going to have improvement on expectation, not in every iteration, but we're going to have an expected improvement until some points, and afterward, we're going to converge to that ambiguity ball determined by this guy. Okay.